Here's something really useful. It's called the Tower property. It's because they found this in the Tower of London a few years ago. Sometimes it's also called the law of total expectation. The law of total expectation. And I think when you see it and think about it, maybe it'll be sort of reminiscent of the law of total probability. Okay, so it goes like this. So for any random variables x and y, the expected value of x can be written like this. Okay, it's the expected value of x given y. Now, of course, that's provided that the expectations exist. Now, this looks complicated, but it's really kind of, I think if you think about it the right way, it makes a lot of sense. Okay, so look at this. This is the expected value of x given y. Now, if I let y take on, if y is actually a random variable and it's not fixed, it's some number, then if I sort of integrate over all the possible y values, if I sort of average this conditional expectation over all the possible y values, then it sort of makes sense that it should be the overall average. What this sort of says is that the average of the averages is the average. Okay, let's prove this in the condition for the continuous case. The proof for the discrete case is similar, except it uses summation signs, of course. So, all right. So this is proof continuous case only. Okay. So I can write the expected value of x as the integral over the reals of x times marginal of x dx, right? Of course that's true. Now, at this point, what I'm going to do is, inside here, I'm going to replace the marginal of x with the integral of the joint density. Right? See, all of this stuff right here is all of this stuff right here. Right? See, if you take the joint density and integrate out, so to speak, the other variable, the y variable, it gives you the marginal density, right? Okay. So now, at this point, I'm going to say that all this is, you know what, actually, let me change this integrand inside this integral. Integrate inside here. I'm going to change this. I'm going to re-express this as the conditional density of x given y times the times the marginal of y, right? And still with respect to y, dx. Okay, so just so that we can sort of keep track of everything that's going on here, this is still all the stuff in the big red box. But I've re-expressed this joint density as the product of the marginal density for y against the conditional density for x given y. Okay? Now, at this point, I'm going to pause and take a break. Okay? Because I'm tired. No, actually what I'm going to do is I'm going to move up here. Okay? I'm going to move up here because I'm out of space. And I'm going to play a trick here. This is the trick that you always want to think about when you see double integrals or triple integrals or double or triple summations or whatever. I'm going to change the order of integration. Okay? I'm going to do that. So when I swap those integrals, I'm going to get this. Right? I'm just going to integrate with respect to x first, and then with respect to y. Okay. Now, when I do that, notice that. So I'm going to have to pull all the integrand stuff inside this inner integral that depends on x. And what is all that stuff? It's x times the conditional density function of x given y. but I can actually pull the marginal of y out, okay, because it doesn't depend on x. Right, so I've got all of this stuff, okay. Now, what is this integral in here? Well, glad you asked. This is this. This is just, isn't this just the conditional expectation of x given y equals little y? Yes, it is. It's that. Okay. And then, so this is, so we've evaluated that integral with respect to x. There's that. And in fact, this is exactly what it is, because here we're done, right? Because look, what this says to do is to average with respect to the density of y, all of these things, right? You're taking the expected value. You just take this and put anything you want there. Put an h in its place. Then you'd have the expected value of h with respect to this y variable. Okay, so this is in fact the expected value of x given y. Okay, now we'll see an application of this. All right, here's a nice little example for you. You see stuff like this in the books. A miner is trapped in a dark cave. Okay, he's here and he's sad. He's going to choose tunnel number 1 or tunnel number 2 or tunnel number 3 with probability 1/3 each time. It's really dark in there. He can't see his way around. He's just sort of aimlessly wandering, but he's always moving. So each time he winds back in this area in here, he then moves to tunnel number 1, which takes him right back to his starting point in exactly 4 hours. He'll take tunnel number 2 with probability 1/3, and that tunnel will take him right back to his starting point in 7 hours, or with probability 1/3 each time he chooses the great tunnel to freedom, which will lead him there in 3 hours. Again, each time he returns back to the cave, it's like he flips a 3-sided coin, right? And picks one of these routes at random. And what we're interested in is his total time to freedom, or you might be interested in the distribution of time to freedom, or simply can we find maybe just the expected time to freedom? Okay, sure. So what we want to do is ask ourselves, what information would it be great to have if we knew some kind of information at all? What kind of information would that be that would make solving this problem easier? A common trick in solving problems like these, or like other kinds of problems, is to condition on the amount of time for the first trip. Okay, so what we can do is use that tower property to write that the expected value of t is the expected value of the expected value of the expected value of the expected value, no, just kidding, of t given f. Where here I'm going to say f is the random time spent on the first trip. Okay, if he picks, for example, if he chooses tunnel number 1, he's going to spend 4 hours there, right? If he chooses tunnel number 2, he's going to spend 7 hours. Okay, so then I can write this as let's see, it's the expected value of these kinds of things, right? So this will be the expected value of t given f equals 4 hours times the probability of that, right? Which is plus the expected value of t given f equals, could be 3 hours, right? times the probability that f equals 3 hours, plus, sort of going out of order here, expected value of t given f equals 7 hours times the probability that f equals 7 hours, right? So this is for, I guess this is for if he chooses tunnel number 1, this is if he chooses tunnel number 3, it's that case, and this is for choosing tunnel number 2, right? Okay. Makes sense? Yeah, you bet it does. Now, hey, guess what? This is just a third, right? And this is just a third, and this is just a third. So all this is just a third times expected value of t given f is 4 plus the expected value of t given f is 7 plus the expected value of t given f equals 3, okay? Now, third times, what is the expected value of his total trip time given that his first excursion takes 4 hours, right? Well, let's see. So let's look back at the picture. What's the expected time to get out of the cave if his first trip is 4 hours? Let's see. Think of it like this. It's sort of memoryless in a sense, right? Every time he comes back, he has no memory, really. I mean, he does, of course. He remembers that it's taken him a long time, but in this little model here, he doesn't get sad or weary or distraught or discouraged over the fact that it's taking him forever to get out of this cave. Yeah, every time he comes back, he picks the next tunnel independently and with probability 1/3, and independently of the past, right? Yeah. So the expected time then, I think, given his first trip goes this way, is just, I think it's going to be that 4 hours plus just the expected value of the time to get back out of the cave, right? Yeah, because it sort of starts over, doesn't it? It sort of starts over when he comes back. And then so plus, by the same kind of reasoning, 7 hours plus ET plus, now the last one here is a little different, isn't it? What's the expected time to get out of the cave given his first excursion was that 3 hour jaunt there? It's 3 hours, right? Period. 3 hours, period. Because then he's free to, then he's been taken to freedom. So this is a third of 4 plus 2ET over 3 plus 10 thirds, right? So that's, what is that? That's 14 thirds plus 2 thirds times the expected value of t. Now remember, all of this stuff is equal to, what was it equal to? It's equal to ET. All of this stuff equals ET. So that means, well, let me just write it here. The expected value of the time to get out is 14 thirds plus 2 thirds ET. Okay? Look at that. So you've got one equation and one variable. Who would have thought it would work out this way? Well, I did. But so if I bring this over, I get a third ET is 14 thirds, or expected time out to get out is 14 hours.